So where in the world does this 4/3 come from when we are calculating the volume of a sphere? So I'll try to give you the intuition and I'll also give you the background on how to figure this out. So here's the intuition. If you have a sphere and you want to figure out its volume, well, it's not very easy to do that because of the shape that it takes on. So now, if you take this sphere, what we're going to try to do is we're going to try to divide it up and break it down into cylinders, so into discs that will start to break this down, and it will look closer and closer to how a sphere would look like. So here is what I mean. So if we have a sphere, and here I'm going to plot in a disc so you can see there that it popped up in blue. So here's another disc, okay, so that you can see there. And what I'm doing is I am taking just simply the radius and I'm moving up the z-axis that I have. And I'm just taking a slice and creating a cylinder, a small cylinder or a disc. And I'm going to be doing that, okay, as I go through, so I can take this entirely. Now let me remove this so that you can see what exactly is happening. So here's another disc, and then here's another disc, and another disc. And you can continue this and find out that you can create all of these different discs. Now, they of course are of a certain height that we have in here. Now, so for this, now if I bring back the sphere itself, you notice that the discs have covered it up. Now, if I could, so as you can see there, I'm going to just let it rotate. If I could just take the cylinders and then just add their volumes, I would probably come relatively close to having the actual volume of the sphere. And that's exactly what the intuition tells us. So now if I pause this for a moment, okay, so let's do that, and let's come back and talk about, okay, what we might want to be able to know in order to figure out this 4/3, or moreover, to figure out the volume of the sphere. So now, what everyone should know, or at least what I'm going to assume, is that you are familiar with the area of a circle. So now, of course, the area of a circle is just pi times its radius, whatever that radius might be, and that radius would be squared. Now, if you extend this up, and if you want the volume of now a cylinder itself, or just a disc, now cylinder is basically nothing else than a disc. So now what we have is just the height, okay, of it wouldn't be very big. So if I take this, and I'm going to draw this out, so for ourselves, so here if it's a cylinder, and this particular cylinder is going to have a certain height. So if you have a cylinder like this, then the volume, again, so you should be familiar with this, that would be the base of the cylinder, so that particular base, and it will be multiplied by whatever height this would be at. Now for us, the base is a circle, so what we have is we need the radius, so this would have been right there, and that's what we would have been dealing with in terms of the base itself. Now the height, of course, would just still be the height, and I'm going to designate it just simply by h, and that would have been the height of this. Now, so if you're familiar with these two things, then you can start thinking about, okay, well, what I'm going to be doing is I'm going to be adding up all of the different cylinders that I have. So I might have one volume of one cylinder, of the second cylinder, of the third cylinder, and this continues on, of course, until you sum up the volume of all the cylinders. And that should approximate the actual volume of your sphere just based on what we have. So if I go back into this and into the simulation, so if I let it continue to spin in here, so what we would have in here, let me maybe pause this along. So instead of doing this, I'm going to now kind of remove all of this, what I have in here, and I've created, so for myself, so here, and let's do that all the way around. So now we have, okay, so as you can see there, so a bunch of cylinders, you can cut away the sphere, and now we can add all of them up. Now, the volume of itself, so within here, we actually have 20 pieces. So if you would count them up, you would have 20 cylinders and it would approximate. And what I have done is I have actually taken this, so let me maybe collapse this through here, And you can see there on the left-hand side that I have the volume of the disks and I'm adding them up. So that formula that you have, so I'll explain that momentarily. And then at the bottom, you have the volume of the sphere, which is actually the 4 over 3 pi r cubed. Now notice, it's still pretty far apart, but it's relatively close. They're both 4. Now the only thing is just the decimal values differ. So what I'm going to do now is, well, what if I could do a much better approximation in here? So instead of having, 10 or 20, well, let me change this up, okay, and double it up. So within here, let's see what happens here. Well, that looks much better. So we have now quite a lot of these cylinders in here, so these disks that I have, and it's approximating this, looks like it's much better. Now let's take a look here. So if I scroll down and I compare, and yes, indeed, so it's gotten closer, okay, than what it was before. And now you can continue to play this game. So this is really the intuition that you have. So I'm going to take this now and again, double it up. And, so within here now, it's going to be very difficult for our eyes to catch this. But as you can see here, so we're now approximating this closer and closer and closer together. And that's exactly what we do in mathematics. So really, we're just going to be adding it up. And what we're doing is, we're just reducing that height of that cylinder where those disks are getting thinner and thinner and thinner. And then we're just adding them up. And if you continue that, where that height just gets infinitesimally small, so it gets smaller and smaller and smaller, you're going to get a much better approximation. Now, within this simulation under Desmos, we might run out, okay, so within here, although I'll try to push this, okay, to let's say, 100, okay, so this would have been almost like 200 of these slices. And let's take a look if it's actually going to do that for us. All right, so it took a little bit of time, but notice that we have pretty much now a beautiful sphere, okay, within here. And so our approximation, so this is now n with 100, well, it's gotten way, way better. So now what I'm going to do is I'm going to actually remove this so that we don't see, okay, so the actual spheres and the cylinders itself, just so that it can calculate this for us much faster. So let's move this, to 1,000. And if I take this to 1,000, okay, so now notice we get 4.1919, etc. So it's getting closer and closer to that volume of the sphere. And notice that the radius is actually set to 1 in this example. Now, if I push this even further, so as it calculates through, okay, so as you're going in there, well, this is pretty close. Now you might ask, okay, so, but what about this 4 over 3? Of course, this is just the volume of the cylinder itself, and these volumes seem to be aligning. They seem to be converging to the same thing. So if I keep cutting up into smaller and smaller pieces, and keep adding them up, then I would do that. Now, by the way, that formula that you see there, the 2 for the disks, just means because I'm doing both, the half a sphere up and then half a sphere down, so that's twice. And I'm just counting up, okay, the actual radius itself. And those numbers, the summation, okay, that you'll see there, so I'll explain that in a few moments. So now that we have this, I can of course keep approximating. Now, if I wanted to be able to see if it really is converging to 4 over 3, now remember, 4 over 3 would just simply be 1.3333, etc. So what I can do is I can take the volume, okay, itself, and I can divide it now by pi, okay, multiplied by r cubed. And that would take, so the volume that you have in there, of course, is 4 over 3 pi r cubed. So if I divide by pi r cubed, it's going to get closer and closer to that 1.333. And notice, so this is only about 10,000. Now, of course, you can go to 100,000, a million, right? You can just making it smaller and smaller and then just keep adding them up. But it's already 1.333. Okay, it looks like it's a 4 there, and then it's a bunch of 3s. So it approximates relatively well. This is where this 4 over 3 comes from, right? The pi, the r cubed, so cubed because it's 3 dimensions, people kind of understand the pi because it's a circle, but then the 4 over 3, kind of how did it come about? Well, now you can get that gauge. And it's pretty interesting that you can see this, as you're going through in here, of course, through the various simulations that we have done. So, as you take a look at this, and as you look at, these pieces and disks, okay, that are beautifully now capturing this, let's see the actual math if you're interested in exactly where that is. And yes, we're going to need a little bit of calculus in order to solve and make this happen. So if I go back in here, so let's take a look and break it down. So how are we summing up all of these various disks? So I told you that we have the volume of these cylinders. That's what we have. So now if I take this entire thing, that's exactly what we want to be able to do. And we're going to be doing this for all of the cylinders that we have. So this is just one cylinder of a particular height. So if you're moving along, so what I would want you to recall is the following. So in 2 dimensions, if you take an equation of a circle, it would have been x squared plus y squared, and it is equal to some radius that you have, and that radius would have been squaring. It would have been nicely drawing you, this nice beautiful circle in 2 dimensions. Well, if you extend this to 3 dimensions, then this is going to become x squared plus y squared. And now we're going to need a 3rd dimension, so let's call it, z squared. And this is, again, going to be equivalent to some radius squared. So now, where do these cylinders come from, and what are we exactly going to be doing in here? So let me just draw it out for us, and let's come back. So here are our cylinders. Now I simplified it so that we don't have a lot of them within here. So these are just captured a few of those. And it is kind of in 2 dimensions. Now notice what I have is I have my z-axis, or my z-axis, which is going upwards. And then, our y is actually pointing out, or in your case, it's pointing out of the screen there. Okay, so that's what you see right here. And then you have your x-axis. So these are our cylinders. So if you take one of these, this basically looks like a cylinder within here. So it has a certain height. So this would have been the height that we have in here. And it has, as its base, a particular circle that we have. So, well, let's break this down. So this would have been this particular height that we have. Well, it's going to project a certain radius. Now notice the radius changes in these cylinders. So this particular cylinder has a different radius than this one, then this one. Notice that it gets smaller and smaller, and that will depend on where it is along the z-axis. So that's what happens there. So if you take a look and you map out this particular volume, well, so this radius squared, so we can certainly substitute that into here, and then this h, really what it is the height, of this particular cylinder. Now that height, instead of writing h, what I'm going to write instead, we very often in math will write, because it's some small value, so that particular height, it's going to be some delta z. Delta just means it's a small value, it's some change that we have. And moreover, we can also write this as dz, like this, where it's that little bit of a change that we have. So ultimately, what we're doing is we're taking this volume and now we're writing it out. So let me do that within here. So I'm going to have pi. Now my radius, so I just want you to kind of keep this, I'm going to write it out in full. So within here, so this is my radius, and this is radius squared that I have. And then this is going to be multiplied by the height, which is going to be some dz. Now this radius over here, well, if you were looking in 2 dimensions, so that radius, or radius squared, would have been nothing else but simply x squared plus y squared that you have. But now we're in 3 dimensions, so it is dependent on this particular variable, because it will depend on what it is, and as you're getting higher and higher, the radius decreases. So how do we capture that? Well, what we can do is we can still have x squared plus y squared, which is the projection onto that axis, and then we can shift this over on the other side. So now what's going to happen when it shifts over? I'm going to stop writing radius, and I'll just simply put r squared, so that's this right here, and then when you shift this over, this is going to be z squared. So your equation that you have is now going to be x squared plus y squared. Notice this is the 2 dimensions, and it's equal to the radius squared on the right-hand side. So really, all of this is just simply the radius squared that we have, and it changes depending on the z, or the z that we're moving along? Well, if we're at the bottom, then z is just 0, and then the radius is r. But if we move up a little bit, and in this case we're moving up by some height, so some delta z, then it's going to change. It's going to be reduced. Notice the subtraction there. So instead of writing this radius that we have in here, so we would write pi, and in here, so this, because of the squared that we have, so we don't have to do anything, we would just simply write, this is going to be r squared minus the z squared, and we're substituting that in. That is equal to the radius squared, and then multiplied by the height itself. And now, this just captures one of them, but we want one cylinder. So that would have been capturing 1, but now if we move up, that will be capturing 2 and 3 and 4 and so on. And if you make them smaller and smaller, okay, then this will change. So we need to add them up. Now I'm going to only add them up, so from here to here. So this is going to be for the, I guess, kind of semi-sphere or half a sphere, okay, that we have. So halfway. So I'm going to be adding them up, and then I have to multiply by 2. So I have to add all of them up. Now the symbol that we use is the symbol. So here's the summation symbol. And this is indeed in calculus, and you might recall this is integration. But all we're doing is just adding up these cylinders. Now I'm going to go, so since I'm starting from 0 over here, and then this is going to go to some radius r all the way up. So here I'm going to start from 0, and I'm going to end up at r. Now keep in mind I need 2 of these because I need the top and I need the bottom. But this 2 I can come back to later. So now in terms of mathematics and this calculus or integration, well, you should now understand the intuition. You saw it visually, right? And I hopefully convinced you that as you made the height smaller and smaller, which means you had more and more disks, okay, you could see that it actually tended towards the exact volume of a sphere, or in other words, that 4 over 3 if you wanted to be able to be convinced by that. Now, if you want to see now the actual calculus part of this, well, really, we're just adding these up and we're making them as small as possible. So we call them infinitesimally small, okay, these little changes, and that is our change over here. That's the actual height, okay, except we're making it smaller and smaller and smaller, okay, so it just keeps going, 10,000, 100,000, okay, million, 10 million, billions, and so on. So now, if you do this, you can certainly take out, so notice that this pi won't really do much for us, so I can bring it outside because it's a constant. So what I'm going to have is just 2 pi outside. And then what I have is I have the integration, okay, between r squared, notice this dz, I'm going to bring inside of here, so that's going to be multiplying, so r squared multiplied by the height, minus, okay, and then also the summation between there of z squared and times dz. So what I have done is I've brought this in, and I have brought it in or distributed across right there. And now I am doing this from 0, okay, so right here, all the way up to r. And now this is the integration component. So now we're integrating with respect to our z, because that's the only thing that's changing. So this r is actually constant. So what you're going to have is you're going to have r squared, and this integrated, you would have had z. And now we're going to now, again, so sum it up between 0 and r. And here, if you do that, so from your calculus a little bit, this is going to be nothing else. Well, this is 0, so this is just simply going to be r cubed. And now over here, what you're going to have this, if you integrate that, you're going to get 1 over 3, and this is going to be z cubed. And again, you're going to be doing this, okay, between 0 and r. So the 0 is gone. So really what you have, now don't forget your minus, you're going to have 1/3, and this is going to be r cubed. So this just comes out to be 2 over 3 r cubed. But hold on a second, you have this 2 pi right in front. So 2 pi, if you multiply, well, that's going to be 4 pi divided by 3 times the radius of that particular sphere. And there you have it. So this is very commonly seen, but what I wanted to do in this video is hopefully convince you that you can see it visually in this way, so that you can have a nice, beautiful picture of these cylinders and an intuition how it actually works. And you can, of course, change this up and make it, thinner and thinner, meaning you can have more and more cylinders as you please. So here it is. and you can keep them. So this is now 20. So that would have been actually times 2. So that's 40. You can even make it even further, and it just approximates beautifully the actual circle itself. So here it is. That's what you have there. And at the bottom, you notice that it's going to be tending towards exactly that 4/3 or the volume. So I hope that this video helps you. It's probably a little bit longer than maybe some other ones, but it gives you kind of a step-by-step that you have in order to understand this. And if you're a teacher or a student and you're interested in simulating this on your own, I'm going to leave the code for you in the video. So you can go down to the description, okay, and take the code, plug it into Desmos and play around with it or show your students as you like. Thanks for watching. All right, welcome to the 1 Million Journey channel. Bye, everybody.